Hello, everyone. My name is Philogy. I'm a developer, Huffathon, and auditor, also co-founder at DREG, small security startup. And today I'll be presenting WETH, one of my longest-standing and favorite side projects, which is essentially a rewrite of wrapped ether. Um, I'm going to be using a lot of like Breaking Bad memes here because meth. So let's get right into this. Let's cook. All right. So quick overview of this presentation. I'm going to be talking about wrapped ether, why it exists, and why it's bad. Then I'll be talking about like what meth is and how it's better. I'll do a basic gas comparison between the like main methods, and then I'm going to talk a little bit about my roadmap to bringing meth to production. So first of all, why wrapped ether exists and why it's bad. Bad is kind of an exaggerated term. It's more that it is suboptimal. Let's say it like that. So first of all, why does wrapped ether exist? So let's have a look at assets in the EVM. There's two main categories. There's like custom developer-defined assets, which are ERC20 tokens, NFTs, vault shares, which all live under contracts. And then there's a sole exception to this, which is ETH, which is the quote-unquote native asset of the EVM. So the special thing about ETH is that you can set it along with calls, you need it to pay gas, and it's also like probably by value one of the biggest assets that lives on the Ethereum blockchain. Not probably, it is the biggest asset that lives on the Ethereum blockchain. And basically the goal of wrapped ether is to bridge these two halves, right? So wrapped ether is just a token contract as well, but its main purpose is to wrap ETH in and out. That's why it's called like wrapped ETH. And that's why meth is called meth, because it's like the W turnaround into M and then ether. So that's why wrapped ether exists. So for better context of like what wrapped ether exactly does, like this is an implementation of wrapped ether in like less than 10 lines. Technically, there's some boilerplate missing because you got to override the name and symbol for Solidity, but this is basically it, right? And this would probably already beat the existing wrapped ether in many benchmarks just because it's, newer compiler version. It's using Solidity, which is already pretty optimized, or not pretty, it's very optimized for Solidity code. So yeah, that's roughly what it does. It just allows you to create tokens when you deposit ether and take them out by burning tokens. So the first reason why wrapped ether is bad is like, imagine you're writing a bridge contract that uses permit or any actually function that is like non-standard. So what you would expect to happen here with wrapped ether, which doesn't have a permit function, is if you call it like this, it should fail, right? It should tell your contract to stop and it's fine. But what actually happens is that it silently passes. And the reason this is because wrapped ether, the popular version that's used on mainnet called WETH9, it has a fallback function. So what this fallback function does is it accepts any call. Doesn't matter what call data, what selector. If it doesn't match one of its functions, it'll just accept it as a deposit, as a call to deposit. And what deposit does is, it wraps ether, but if you don't send any Ethereum with it, like here, it'll just think, oh, it's a deposit for 0, and just like silently pass, as if you're calling deposit with amount 0, which is what you don't want. This actually led to an exploit of a bridge, which is why it's called bridge stuff. It's inspired by that hack, where you could steal funds from others by plugging in the wrapped ether address. It would ignore the permit and let you transfer from other people's addresses. So that's like the first foot gun. And it does wreck you. Okay. So the next reason why wrapped ether is not bad, like going off that, is it doesn't have the ERC 2612 permit standard. So this standard allows you to sign approvals. So instead of you having to submit a transaction, you can sign a message, and you can submit this message either yourself with a transaction, so you can do like approve and interact in one transaction, or if you want to do like an asynchronous bid, or if you want to do an asynchronous or gasless transfer. But wrapped ether doesn't have this. So the consequence of this is you need at least 2 separate transactions to start doing anything related to wrapped ETH on the chain. So again, because of the difference between like native ETH and other tokens, you can't asynchronously withdraw ETH from other people's wallets. There's no permit scheme for that. So that's what wrapped ether handles for you. But to use that, you need at least 2 separate transactions, and sometimes 3. Like if you don't have any wrapped ether, imagine you want to do an asynchronous bid on Seaport, for example, and you don't have any wrapped ether yet. You have to do 1 interaction to get some wrapped ether, a second one to actually approve the main contract to actually spend your wrapped ether, and then third, you have to sign the bid or submit the transaction for the bid. So ideally, this would be like 1 interaction, or at most 2. So this is, not only annoying UX-wise, but it also wastes a lot of gas. Like every individual transaction costs 21,000 gas. So next, as I mentioned before, it doesn't allow you to do gasless transfers or other fancy things. And this is also basically the reason why permit 2 exists from Uniswap. I mean, there's also other tokens that don't support permits, but this is like the biggest one. And permit 2 is meant to be like this universal bridge where, yes, you still need 2 interactions, but if you just approve permit 2, and assuming your DeFi application also supports permit 2, which is basically nobody except for Uniswap right now, then you can, in theory, save like these 1-2 interactions. So this has me feeling like this as well every time I want to use SEPA or anything, and I gotta interact with wrapped ether. So yeah. And the last, and in my opinion, most important, but probably objectively the least important reason is like gas bad. So wrapped ether, the current implementation is suboptimal in many avenues, and I'll get to how I improve them individually in a sec. But basically, there's no permits, right? So you got to spend extra gas for these individual transactions. There's no shorthands for common actions such as deposit transfer plus withdraw, and all these things. And the reason you want shorthands for these is that not only do you have like the added overhead for the function call, if you've got to do 2 separate calls, it's also potentially the transaction overhead of 21,000 gas, and it's the intermediary like accounting overhead, right? So if you do deposit, it'll update your balance, and then when you transfer it away to somebody, it'll update your and their balance. Versus if you could just directly set their balance, you could skip your own balance update entirely. Or in the withdraw case, if you had these combined into one flow, your contract wouldn't need a fallback function to accept ether. You could just directly send ether to the destination by spending your balance. So these efficiencies are like really lacking, and for a contract that is as used as wrapped ether, like for context, wrapped ether consistently uses like 2 to 5% of all gas on Ethereum. And I'm not sure how those stats are compiled because they're difficult to compile, especially with the way like data tooling is right now. I think that's only top level calls. So that's not even including like the internal calls that like Uniswap and Seaport make to these contracts. So it uses a lot of Ethereum's gas. So this is quite an important contract. And even, just saving 1-2%, which is what METH does, and even more in certain instances, will lead to millions of dollars worth of gas saved for users. And another reason like wrapped ether is not that great is it's been written quite a while ago. It's quite an old contract, so the bytecode that was generated by the compiler back then is obviously like not the best. Every time I have to look at the Uniswap router and see what transactions are being made, I'm thinking of my contract and my optimizations, like how these users, are basically, unfortunately, wasting money, at least right now. So let's cook some meth. Let's finally get to the actual project now that I've roasted WETH9 a bit. I mean, it was a great contract for the time, but I feel like as an ecosystem, we've matured a lot, and it's time for the next thing. Okay, let's get cracked. Let's cook some meth. So I'm going to go through the optimizations. It's going to get kind of technical, not kind of, it's going to get pretty technical and low level. So get strapped in for this. This is where the alpha is. So, and I split my optimizations by unhingedness, right? So level 1 and 2 are like kind of normal still, and level 3 is where it gets kind of icky, and level 4 is like where some people might not be okay with it anymore. But there are trade-offs, there's justifications for it, and I'll get to them in a second. So the first one is high-level optimizations. So these are the most important always when you're optimizing for gas. And if you look at like big optimizers like Harrison, you'll rarely see him talk about inline assembly, let alone Huff. It's because gas optimization follows the Pareto principle, where the majority of savings comes from like these simple high-level things, and then you can squeeze in the remaining 20% with these low-level tactics. But really, the majority comes from that, and it's the same with the METH. So we add permit, which can save you 12 to 15k gas on interactions. And we add combined functions, as I mentioned before, for common things. So these are how they're called. And there's a bunch more of them, like withdraw from 2. There's withdraw all 2. And we have a simplified storage layout. So hashing is relatively expensive. It's like 30 gas plus 6 for every word. And the way Solidity does mappings is it basically hashes for every level of nesting. So for the allowance map, I just hash in one go, the owner and spender together. So this already saves some gas. And I pack the balance and nonce together in one slot. Technically not yet. I used to, and then I removed permit, and I'm going to add it again. So at this moment, I'm not doing that just yet, but I will. And the storage slot scheme for this value is just directly taking the address, no hashing at all. So obviously this is super efficient. And the reason I can do this relatively safely in this contract is that a collision between a hash and an owner is relatively difficult. and you assume there's no collisions between addresses anyway, right? So you can use a scheme, and I don't have any other storage. There's no slot for total supply. That's also to save gas. Actually, I forgot to mention this here, but yeah. And ironically, some of the gas optimizations that I borrow here were originally not in Meth. I actually was reviewing the WETH 9 contract, and a lot of things are borrowed from it, like the fact that there's no independent total supply variable. It just returns the ETH balance that it has, which is technically not correct, and that's why some security researchers a few months ago, or maybe it was even a year ago, claimed they quote unquote found a vulnerability in wrapped ether. This was because you could self-destruct ETH to the wrapped ETH contract, increasing its stated total supply while increasing none of the balances. So that's like technically like a soft invariant violation. And Meth will have this as well, but it's not actually a real issue. Like it doesn't allow you to steal funds. It doesn't allow you to manipulate balances or allowances. So it's completely fine. And the most important thing is it lets you avoid updating the total supply when you deposit or when you withdraw, which is very big. It's like 5K. Yeah, it's like 5K plus gas every time. So it's very huge. So let's finally get to what you've been waiting for. Probably is let's get to the Huff. All right, let's get to the low-level optimizations and really diving into things. Sorry, just grabbing some water for a sec. So, Huff, our wonderkind. So the first low-level optimization is just cleaning up the bytecode. So if you look at the deposit function of the two, like Meth on the left, WETH 9 on the right, WETH 9 has a lot of instructions, and it's not even the whole thing. Like I've had to cut it out because the screenshot was just gone very long. Versus Meth, it's just like counting it, it's like less than 50 instructions. I mean, obviously excluding the function dispatcher, but also excluding on the right side. So it's super minimal. It's like basically just the minimum possible. So you can, that's what Huff allows you to do. That's the thing you can actually only do in Huff is you can get really clean minimal bytecode because you control every single piece. And that's what I did with Meth. I've rewritten all these methods from scratch in bytecode, making sure that every single opcode is optimized. I've often done like, almost entire refactors because I found a way that it would save me like 6 gas. So there's been a lot of effort put into making this really optimal. And if you're interested in how I created this view on the right, it's like actually a pretty cool tool where you can see like a graph. It's called bytegraph.xyz. Highly recommend to check it out if you just want to have an insight into like what bytecode looks like for larger contracts and like rough look at the control flow graph. So in general, when I'm cleaning up bytecode, and what you can watch out for too is like try to eliminate swap and pop instructions almost completely, especially pop instructions. And swap instructions are only rarely actually necessary because basically what a swap does, if you think about it, it's not logic and it's not a condition, it's not a branch. The only thing it does is it rearranges variables. It's basically like swapping two variables. If you imagine your stack positions are variables, so it doesn't do anything functionally. So if you can avoid that, and you often can by just planning things out in advance and making sure variables on the stack are laid out in the right way in the right time, you can eliminate almost all swaps. There's like very few swap instructions in Meth, and that's only because there's like no feasible way how you can organize a stack just because of like how things are computed. So yeah, try to eliminate those. Next is like simplify computations and branch logic. So this is something Jay Trilly mentioned in his talk the other day, but like look at the popular like compiler optimizers like Solidity and Viper and see what are they doing. They're it's so-called like peephole optimizations where they will scan for certain sequences of opcodes and replace them with other sequences. And you can apply this to your bytecode as well. And I've done this in a lot of places. I mean, I haven't actually looked at the compiler. I probably should, but I did this manually everywhere. But yeah, you can replace certain sequences with simpler operations. And the thing is, I didn't have to do this a lot, at least in my case, because most of the operations are pretty simple. It's like additions and subtractions. And sometimes there's like a few interesting ways how you combine logical expressions, but I'll get it done in a sec. So one example how I simplify things is if you the call value check, instead of having an is0 and then jumping, you can just like remove the is0 by flipping things. So, and another thing you can do is you can avoid expensive computations by duping. This is relatively standard. If you have to load something from storage or calculate something, if it costs more than 3 gas, just dupe it. Another thing is like you can save 1 gas by using certain opcodes to push values like 0. So The reason I'd still recommend using return data size and call value in your contracts, although you have to be careful with both of them, is that push zero is not supported on all chains yet. So while it is more convenient and more safe, call value and return data size will often allow you to do the same without having to worry about cross-chain incompatibilities. And M size is actually pretty cool, and I think kind of underrated because I don't think a lot of people know M size because it's like disallowed in inline assembly unless you disable the optimizer completely. So you don't see it often, but basically it's an opcode that kind of simulates the Solidity free memory pointer, but there's like crucial differences. But at the beginning, it'll give you 0 because no memory has been allocated, and it'll basically tell you like the size of memory. So if you're having to return something or organize things for an event, then M size is really useful. All right, keep getting some water. All right. So in general, my philosophy with optimizing in Huff is think about the minimal bytecode and try to get your code to it. So by minimal bytecode, I mean imagine remove all the variables, remove all the branches, and just think about the pure logic of your code. What is it doing? Like let's say the transfer function. You need to change and check one balance and then update the other. So what are the minimum operations, assuming you can just magically teleport inputs where they need to be? What are the minimum opcodes? You need two S loads for the slots, you need two S stores, you need a greater comparison, you need an addition and a subtraction, and then that's basically it. And then you can start adding all the necessary, what I call like piping of your contract of like, okay, how do you actually get your control flow there through the function dispatcher? How do you actually structure the check? Is it a branch? Is it something else? And this will help you get some really good clean bytecode, because if you're going down to the level of like basically zero abstractions of Huff, although Huff does offer you some useful abstractions with macros and the functions that allow you to push event signatures and stuff, but you're basically in zero abstraction land. So if you're gonna put yourself through that trouble, you should use it to its fullest extent and really put in the work to get optimal bytecode. Yeah, science. So the next part of low-level optimization, which is I think especially important once you're down in this like thinking about not in terms of dozens of gas, but like literally individual gas, is branches. Branches are really expensive, and as a comparison, like a single branch will cost you at least 13 gas because it's 10 for the jump I instruction plus 3 for the push of the label. Right? Compare this with a bitwise or n or is 0, it's just 3 gas. And so this means that if you have like a bunch of requires in your Huff contract, which are some check plus jump I, you can actually combine these into one branch and save a lot of gas doing that, because combining two logical expressions is maybe just one of these, or at most 2, and in worst case 3, but usually just 2 or 3 of usually just 1 or 2 of these instructions, which is 3 or 6 gas versus 14 gas for having its own branch. And then that's what I do in Meth as well. So for example, the transfer function, it has only a single jump I. It has a jump for the dispatcher, and we'll get to that, but it only has a single condition. This condition checks the selector matches, it checks the call value, it checks that your balance is sufficient, all that in one single jump I. And this actually saves, at each step like 6, 9 gas. And then these two are just there for comparison. And I want to mention this EIP a few times in my talk, EIP 4200, to get people excited about it, because as an optimizer, this EIP can save us a lot of effort. Like all this weird thing around how we have to combine logical conditions to save on branches will not be a thing anymore with EIP 4200, because it'll change the jump opcodes to be relative jumps and also change the pricing. Because now they can't be dynamic anymore. There's no like label, so you don't have to push a label. That's 3 gas less. And the actual branch only costs 2 gas. So that's basically 12 gas saving for every branch. And this actually changed the trade-off. So now you don't want to minimize branches. You actually want to minimize combining conditions into one. And this also allows you to add back in custom errors. Because, for example, because of this trade-off of the branch versus the logical instructions, Meth doesn't actually have custom errors, because it would cost gas to have a different require for every single condition that has its own error. It's all bundled into one jump E. So it means when it jumps to the revert, it doesn't actually know why it jumped there. It just knew that one of the conditions went wrong. So you can't really have a custom error for that. I mean, you technically could. If you jump to the revert instead of directly reverting, you could actually rerun the code to see where exactly it went wrong, whether it's a selector, the call value, or the bounds, for example. But that would be, extra code, extra effort, and extra attack surface where bugs can sneak in. So for simplicity's sake, I just remove that. And especially for meth, there's like it's much more lenient because it's not very complex. So when you're debugging it, I assume as a dev, it'll be easier to figure out like the reason for the revert, like selector call value is like relatively obvious, and whether it's a balance or an allowance that went wrong, that's also not too hard to figure out. So that's why I've done it that way. So furthermore, simplifying branches. So another cool thing to note, or important thing to note, is that jump E will jump on any non-zero value, not only one. So this means that you can, for example, if you want to compare that two things are not equal, instead of doing equal and then is zero, you can do subtraction, right? And these are logically equivalent. Another one is you can transform an and into or. So here I have a bunch of e0s, and it'll rarely be like that. But if you imagine what this is equivalent, is what the equivalent thing of this is that if you have is0 and, you can turn it into an or if you just remove the is0 and invert the x and y. And there's different ways to do this depending on what your x and y are. So this is a cool thing you can do in Huff. And then, as I mentioned before, you can use like and or to combine different conditions. Instead of doing first condition, jump E, second condition, jump I, or jump E. My pronunciation is a bit inconsistent here, but you can combine these with and or. You got to be a bit careful with and, because if your inputs aren't 0 or 1, like if call value, let's say, is one of your inputs to and, it won't actually work because they're bitwise operators. They're not actually logical operators. So you might have to is0 it before or use a different one. But generally, you can use it quite well. And another thing is that if your branch ends in is0, as I mentioned before, you can actually flip your blocks around to remove that. So I do that very often for reverts. And another thing you can do even more, to go even further, is note that the label that is marked by name : it actually becomes a jump test when compiled. And a jump test is not actually free. A jump test costs 1 gas. So it means that the branch in your code where the jump I lands, so like the non-zero part of your branch, will actually cost 1 more gas. So in Meth, I've organized it such that most non-reverting, or like most requires, will jump to the revert. So it's 1 more gas for the revert case, but it saves a gas on the non-revert case. And I'm heavily optimizing for the non-revert case in Meth. So next part is function dispatchers. I wrote a whole blog post about this, but I'm still going to dive into it here. Quick water break, so you can scan the QR code and go to the link, or like save it if you need to. You can also just ask me about it in the server if you don't manage to write it down here. But basically, there's different function dispatcher designs. And Solidity and Viper will generate the first two, although Viper recently added the option to create the third one, and Meth uses the fourth one, but I'll explain all of them. I'll just skim over them real quick. So the first set of them are the linear and the binary search dispatcher, I call them. So the first one, Solidity will make when you don't have a lot of functions. And the second one, Solidity will make when you have a lot of them. So the first one is very simple to understand. It's basically just a big if-else, or like a switch case, you can imagine, where it just checks, is this selector the right one? No, check the next one, check the next one. And the binary search dispatcher splits the possibilities in 2 every time. So it compares your selector to a pivot, which basically splits it into 2 possibilities, right? So that means that at every step, instead of eliminating 1 possibility, you can eliminate half. So this is pretty cool, because if you have more than 4 selectors, this can actually save quite a bit of gas, and it's cool that Solidity does that, but you can push it further. Next part is constant lookup dispatchers. So Viper recently added this. I'm not sure if it's in prod just yet, but this is pretty cool that a high-level language compiler has this. So the basic idea is that instead of checking or comparing selectors, is you first retrieve your selector very normally, as you would with any other dispatcher, but then you look up the jump destination label, or here it's label, but technically would be the destination in a table, and they jump to that label, and then there, once you're at the final location, you would check that the selector matches, because depending on your lookup scheme, which is most of them, it won't be collision resistant, meaning that two different selectors will jump to the same location, and one of those two is likely not supported by your contract. So yeah, ideally you should revert in that case, because otherwise you might end up in a situation where you have a similar footgun to meth, where random selectors that are not implemented won't revert and will trigger the logic of some other function, which could be pretty bad. I'll talk about. I have a whole section here about the footgun trade-off. Like saving gas versus footguns. I actually forgot to include this trade-off specifically, but in meth I did do a selector check, so you don't have the WETH 9 style footgun where you might accidentally call it. That's also just because I was able to get it very low in gas. So yeah. So how do you build up these lookup tables? So there's different ways. There in Huff you have this syntax for jump tables, or jump table packed, which allow you to define a table of like jump labels, and then you can reference it in your code and do a code copy to get the actual label. This is kind of pricey because one, you have to do a code copy, and then you're also doing memory expansion. But it's pretty good, especially for larger contracts. Another one is you can pack all your push labels into a single push value, to a single constant. So this is not yet supported out of the box. So you have to either in the constructor construct this packed value and then insert it into your bytecode, or you have your own script generated. The problem with this approach is that it's kind of limited, because a push can at most push 32 bytes to the stack, and a jump label by default is 2 bytes. So you can get it down, because most contracts don't actually need all bits, so you can get it down to instead of using the full 16 bits, you can maybe 11, 10, or maybe even less bits. You can pack slightly more, and you can do even more if you use De Bruijn lookups. So I'm not going to dive into what De Bruijn lookups are exactly, but the idea is that you can fit even more by imagining that your EVM word is a 256-bit value, and a specific window over it is a label, right? So that means that if you just move the window by 1 bit, it overlaps with the last window, but it might represent a new unique jump label. And this way you can pack many more into just one value. And this is actually how I originally built the meth dispatcher, until I found an even more efficient way, which I'll get to in a second. So, and then how do you actually look up in these tables, right? You can create a table to store your jump labels, but then you have to actually index into them. So there's different ways. Hashing you can do is probably the easiest, because you just have to mine a salt that'll get you a unique index for every one of your selectors. The problem is, as I mentioned before, hashing is expensive. If you go back to, oh, wait, I jumped all the way to the beginning. Whoops. One sec. Oh yeah, here. So if you look at this table, just as a comparison real quick, I forgot to include a hash. That would have been a cool comparison, but it would have been all the way up here. It's 30 gas. So it's very expensive in Huff land. Let's go back. Whoa. All right. So another way you can do is bit isolation. That's what I use in meth. So you basically look at your selector as a sequence of bits, and then you bit shift it and AND it and OR it to get the unique bits and use that as an index for your table. Or you can create a cheaper simplified hash function. This is kind of tricky. I don't know how you do this in a consistent way, but basically you find some magic value that when you XOR it with your selectors and maybe mod it by some prime, you get a unique index for every one of your selectors, and then you can use that as the index. That's kind of tricky. You just gotta maybe there's an algorithm for it. I don't think so, but it's a trial and error thing, which can be worth it depending on your project. So let's get to meth's function dispatcher, which is actually even better, but surprisingly simpler. So the idea behind the dispatcher is what if we directly read a valid jump destination from the selector? So no lookups. We just do a transformation, a simple transformation of the selector, and that directly is our selector. So let me show you how this works in meth. So imagine there's a bunch of different calls, even one that's not implemented. And then the first step in meth's dispatcher is you feed it through a bit shift, right? Because I want to isolate the top byte. So I push it down, not fully until 1 byte is remaining. I leave some bits, some lower bits, and you'll see why in a second. So I pipe these through the bit shift, and then I pipe this through an OR. So the OR serves 2 functions. One, it clears the lower bits, and unlike what you would typically do to clear bits, which is a bitwise AND, keeping the upper bits, I actually clear the lower bits. And the reason I do this is because this selector down here, or lack of a selector for the receive function, it actually gets transformed to a non-zero value. Because if you imagine that I'm jumping to this label, if I use an AND, it would be 0, right, for this case. And if I jump, and I can't have a valid destination 0. That's where my program starts, right? So by using an OR, I can fulfill both the function of clearing the bits, but also having a non-zero offset for my table. And overall, the cost is like selector retrieval, 11 gas, which you have for any dispatcher. And then you have the destination derivation, which is 15 gas, because you have got to push this constant, shift, push this constant, shift, and you have a dupe at the beginning to duplicate the selector. And then the jump is like 8 gas for the actual jump instruction plus 1 for the jump test. And then depending on how the selector or call value check is done, if it's like independent or combined with other things, it adds 9 to 24 gas. So if you consider that a single if-else here, and a single if-else in the classical selector costs 22 gas already, this fancy like direct dispatcher becomes worth it very quickly, right? So this here is like 24 gas, so that's slightly more expensive than one if-else. But then after like 3 functions, it's already worth it. So this is like a very nice way to do it. So the end result of this dispatcher is that it maps any selector you can throw at any 4-byte combination to one of 256 locations in the bytecode. Destinations are spread in 64-byte increments. So that's the kind of a limitation of this approach, is that your functions have to be spread equally apart. And there's an upper bound to how spread apart they can be, or like how big these blocks can be, because of the bytecode limit, right? So 64 is like actually the upper limit for this. And you can still fit in larger logic because you can just put it at the end, right? So the first 16 kilobytes will just be your function dispatcher. And if any function needs more than 64 bytes, you can just jump to a place where there's padding or thing. Now the jump is more expensive, so I avoid that as much as possible in Meth. But there's certain cases where I have to do that, but I do it I use the condition jump to do that. So it adds basically no extra gas. I think it adds 1 extra gas, but the layout of the dispatcher makes that extra gas worth it. And the cool thing about this approach is that it also works for the receive fallback, right? So if you send no bytes of call data load will default to 0, meaning it'll still work for this, right? We have this receive example down here. If you call data load to get the selector, it'll just give you 0, right? So that's completely fine. And it gives you a valid jump test at the end. And the only thing we have to change is that at the destination, instead of checking the selector, we'll just check the call data size is 0. So it works for that. To save gas, I combine the selector and message value checks together, as I mentioned before, to save on branches. They're packed together. And then these checks are later combined with like balance checks and so ever. So I mentioned this before, but the transfer, for example, function only has 1 jump I. So the main downside of this is bytecode bloat. If you look at this graph, it's 85% of Meth is just 0 padding. It's not actual logic, so the contract is like 16 something kilobytes, and 85% of that is just padding, right? So this will massively increase your deployment costs. But again, because of how used wrapped ether is, if I'm playing on the assumption that Meth will replace it, that deployment cost will be insignificant in comparison to the savings. And again, EIP 4200 fixes this again because it wants to add an opcode for jump tables. So all this bloat, all this thing will be unnecessary. It will be super easy and efficient, and actually use even less gas than it currently does. So it'll lead to smaller bytecode, less gas. So overall, super cool EIP. Please support it. Give it some love in the Ethereum Magicians forum. So the next level of unhingedness in optimizations is removing some classic solidity safeguards. So this is where it gets kind of dangerous. Don't recommend this for all projects. Although I think the trade-offs here are worth it, and I explain them. So first of all, call data size checks. Solidity will check that you give it enough call data, so 4 bytes for the selector plus whatever you need for each ABI encoded parameter. And not only is this call data size check the way Solidity does it not optimal, but I just don't do it in Meth. The reason is the call data size check was added in the first place to save like noob devs who would encode arguments by just like concatenating strings together, which can mess up if you make a string too short and then the one can go into the other. Long story short, it's just like this is not even a thing anymore. Almost everyone that interacts with the chain uses some sort of library like Ethers.js or Web3.js, which encodes everything correctly for you. So I think wasting gas for all normal users to save the one dev who's going to be an idiot, I don't think that's worth it. Also, not having call data size check allows you to save gas by saying that if your last parameter ends in zeros, you can just like omit those and save on call data costs. So that's cool as well. Another thing is that if you send dirty values to a normal Solidity contract, it'll revert. In Meth, it's just cleaned, right? So it's clean where necessary. So this means like if you have an address parameter in your function, in Solidity, if you send like address, so 20 bytes plus like some upper bytes or bits that doesn't actually fit into an address, Solidity will revert. Meth will just clean it and say ignore it. So if you mess up somehow a little bit and send an unintended value there, which is rare, if you use Solidity to interact with this or the utility library that Meth will have, it'll be type checked anyway, so you don't have to worry about that. So yeah, there's only very, very weird edge cases where you're writing inline assembly anyway where this would actually harm you. Next is call value checks. So Meth actually has these because Meth is wrapped Ether, right? So the main use case for it is sending Ether to it. So I think it's very likely that users will, and this has happened before to other contracts, that they will send ETH to it. So I did keep the call value check in Meth. This is also because it only costs 5 gas to keep it. And, it primarily deals with ETH. So I think the losses from users will probably exceed the 5 gas saved for all other users. Yeah. And then 0, this address checks. Meth doesn't do those. The way it deals with those is that it has a special recovery address. And the only ability that the recovery address has is that it can receive funds from the 0 and this address, meaning that if you lose your funds in Meth because you send it to 0 or this, you could like contact the multisig that's behind the recovery address and they can give you back funds, but only from the 0 of this address. So to be clear, Meth is completely trustless. If you have a normal balance, nobody can ever change that from you. It's just that if you accidentally send those funds to the wrong place, you can get them back, but only from these 2 addresses. So the footgun versus gas trade-offs are important ones because you can save quite a bit of gas with the dirty value checks, call data size checks. They do add up quite significantly. And the next class of optimizations are almost also safeguards, and they lead to even more savings. So these are the most unhinged optimizations I'm about to show you. I'm stretching, if not straight up violating the ERC20 spec. So these are kind of sus, but I think they're worth it. I'm going to explain the trade-offs in a sec. So the first one is the withdrawal events. So WETH 9 also does this, but it has custom deposit and withdrawal events. So if you were to implement this contract today with OpenZeppelin, what you would get on the mint and burn would be transfer events from or to 0. So the reason this is cool to have these transfer events is that if you write an indexer or a blockchain explorer, you can just look at all transfer events and very easily track the movement of funds. It's one event that tracks all balance changes. However, this also means that you have wasted index fields, and index fields are expensive, right? So just removing one index field, which is the 0 from or the 0.2, saves 375 gas. So if we go back to our graph where we were worrying and anxious about 10 gas, 375 gas is huge. It's monumental. So this is definitely a trade-off. And if you look at the spec, it's technically fine, right? It says contracts which create new tokens should trigger transfer event, which in spec language means it's a recommendation. It's not a requirement. And it doesn't even say anything about burns, i.e. withdrawals. So this is actually still completely legal within the spec. The next is infinite approvals. They're not even in the spec actually, but all contracts implement them as an infinite approval, basically where it skips updates, is anywhere if you have the max uint. And I set the threshold slightly lower. It's still practically infinitely large, but the reason I put it at this value is that if you see the hex representation of this, it's a 1 with 31 zeros. So this means that if you want to approve somebody to be infinite, you can omit 31 0 XFF bytes, which is 496 gas in call data costs. So again, quite monumental. So the next one, I think this is the most controversial one, and I might actually go back on this one. But transfer from, and approve don't return true. So this saves this is a blatant spec violation. Like the ERC20 spec wants you to return a Boolean. So the reason I do this is because it saves 16 to 18 gas. And also, USDT, a huge token, already does this. And that's why most devs use a safe transfer library, which handles this completely fine. So Uniswap contracts handle this. Basically, all DeFi contracts that have anything to do with like multiple ERC20 tokens handle this out of the box. The only place where this is actually likely to lead to an issue is in for devs that basically import, like, let's say, the Open Zeppelin IRC20 interface and directly use it, because what will happen is Solidity will check for and try to decode the return data, and if it sees that there's zero return data, it'll just revert. So in those cases, you might get a contract that's just stuck. But this is the rarest of cases, and usually you're vulnerable anyway, right? You're meant to use safe transfer libraries, and you're not meant to directly use the contracts for this reason. So I may go back on this one, because this is the only actual like blatant spec violation, and it doesn't save that much gas. But most contracts will handle this just fine. So now some benchmarks. This is an early comparison. Not early, it's not going to get much better likely, but these are just like direct calls, like one-to-one comparisons of doing this in METH, doing this in WETH. So it's not huge. If you look at it, it's like 1 to 4% depending on the method. But it gets bigger, right? So if you imagine it's an internal call, then already you remove 21,000 gas from each side, and the percentage gets bigger, right? So that's one thing. And another thing is I haven't measured yet the comparison of the combined calls, right? If you do deposit and then transfer versus deposit 2, and there you're going to add a few hundred gas again on savings. So this will easily get, in practice, depending on the call, like 8 to 10%, which doesn't sound like a lot. But again, if you think back to that, Ether right now uses 2 to 6% of all gas on Ethereum. The savings for users, assuming like everybody fully transitions, will be in the millions of dollars yearly. Whoops. All right. Small water break. So I mention this all the time, but yeah, Wrapped Ether uses 2 to 6% of all gas on Ethereum. And yeah, already the base savings will lead to millions. So that's the explanation of why I'm doing this. Also, it's not only going to save you gas, but deployment costs, because your bytecode can be smaller, right? If you omit the fallback function, that saves you bytecode, and that makes your function dispatcher more efficient. It's great all around. Also, permits will be great for UX and gas as well. And also, I want METH to be like the first major usable Huff application in production. So Jay really talked about production Huff the other day. But outside of like MEV bots, which are not really like user-facing applications, I don't know of any Huff code base that is in production. Like there's like small proxy contracts that have been like written with Huff, like no major application. So I think this would be a huge milestone for the Huff community, and just like showing the world that, not only Huff is not only like a Tinker or like MEV language, but it can actually be used in specific cases to write like core pieces of like Ethereum infrastructure that people can rely on, and that the gas savings can lead to practical dollar savings for users. And also, I want it to be audited. I mean, it'll have to be audited to gain adoption, I think. So this will also be, I think, the first formal Huff audit. There might have already been Huff audits. Like I think Chain Security recently, when they audited the new like Beacon State Root ring buffer contract, it was in bytecode. So technically there's already been a few audits for bytecode, but not an actual Huff audit, I don't think yet. And especially not at this scale. I don't think there's ever been an audit of bytecode at this scale. As mentioned, the contract is like 16 kilobytes, although most of it is padding, but still. So that would be a big milestone, I think, also for the security community. Next steps. So how do I want to bring this to production? So that was like the why. So finalize implementation. It's not fully done yet. I want to add the 2.6.12 permits, because initially I removed them because I was like bullish on account abstraction, and like I said that, account abstraction wallets are not going to need this. Why add all this bloating complexity? But then I realized, account abstraction is moving, unfortunately, kind of slow, and we're going to have EOAs for a long time, so better add it. Another thing is like adding native swap methods. You can easily exchange one or the other. I think this will make the adoption easier and smoother, because if you imagine Uniswap, some liquidity providers might not trust METH yet, so they'll use WETH 9. And then if you imagine there's not a native method, it'll cost a bit more gas to do like the bridging between METH and WETH, because you have to unwrap the one and then wrap into the other if you imagine a route. So by default, this will like slightly worsen the value of routes going through METH and kind of disincentivize its use. So by adding a swap method, you make this friction slightly less. So I think it's definitely worth it. And then more testing. I have some basic unit tests, but I want to add invariant tests. I've also started working on symbolic tests using HEVM. That's also what I want to do next. I've been working a little bit with working is an overstatement. I've been asking the HEVM team for different features that I've been missing to try and write the formal spec in Solidity, because I'm not a huge formal verifier. I'm not very good with these formal languages yet. So the cool thing about HEVM is that I've been able to so far write a spec in Solidity, which is pretty neat actually. And then next step is a formal audit. As mentioned, it's likely going to be the first formal Huff audit. If there's already been one, please correct me. Please leave me on Twitter. I'd love to know who the auditors were, what they did, and what scale of code base that was. It would really interest me. And that's pretty much it. Check out the GitHub. It's a pretty substantially sized Huff code base. There's other interesting things in there, like the scripts I use for benchmarking, or to help me with the compilation process, because like there's padding in the bytecode, so I have like a debugging script that helps me with that. So if you're interested in that kind of stuff, check it out, and maybe help me get to 100 stars. Thanks for listening. Check me out on Twitter. If you're interested in smart contract security, you can contact me on Twitter or at my email. Thanks everyone for taking the time. Oh, and because this is a legal requirement to using their free templates, credit to SlideGo for the template. It's actually a pretty nice template, so I would recommend them unironically as well. Thanks for coming to my presentation, and feel free to ask me any questions on Discord, etc.